Hello, I'm Andrew Leonard and this is my lab of motion of falling objects. So, what is the goal of this project? It's to analyze a falling object accelerating due to gravity and prove if it's accelerating or not. And we analyze its predicted motion once we factor in drag. We also make a position versus time graph of the movement without drag, of with drag, and the analyzed video, and we compare the three graphs. To analyze, I recorded a paper ball falling from a height and analyzed it using the tracker software. And then I created a model using GlowScript, and I based it off the momentum principle, position update formula, force of gravity, and the force of turbulent force. The results showed a strong correlation between the model and analyzed data, showing a strong resemblance, proving that the object was in fact speeding up. All graphs show a non-constant curved slope, which proves, in fact, the objects were experiencing acceleration. Also, the graph with drag shows how the drag force slows the object down and does not let it move as far in a given time period. So here's my video. And now, for the setup, I chose to use a ball made of 3 paper sheets due to its presumed air resistance. And on tracker, I set the scaling factor as the width of the paper ball, it was 0.045 meters, and set the axis as my starting point of the ball, shown in pink. The analysis, I recorded the position of the ball at 16 equally spaced time intervals, and the ball shows that it was speeding up over the interval. And here are the results. It moved negative 1.135 meters in the y direction in half a second, and it started at an initial velocity of 0 meters per second. Now, scientific principle is used in the model. So, for the model without drag, I had the net force equal to negative mg, but with drag, I had negative mg plus the turbulent force, which is b is the constant proportionality, j hat is the unit vector, and the force is not constant as the force increases as v increases. So as you can see here in the free body diagram, the force of gravity is pulling the object down, but the turbulent drag force is opposing its motion upward. I then use the momentum principle to find out the velocity after a time delta t, and use that velocity to update the position. So using the position update formula, it updates the position of the ball during duration delta t. Now my GlowScript model is simulates how the ball would move in a perfect world. And the initial conditions, the mass I got from Googling the mass of a sheet of paper, and the velocity, position, and time are all from tracker. I calculate the net force, the force of gravity, and turbulent net force, and use the position, momentum principle, and a position update formula to simulate movement of the ball. It prints out time and position values for each time step. So as you can see here, the ball mass is 0.135 kilograms. The position and the velocity are both from tracker, which is they're almost 0. And here you can see the formula for the force of gravity is just negative mg. And here is how I calculate the turbulent drag force, which is then F net is equal to turbulent drag force plus force of gravity. So the gravity is acting downwards and the drag force is positive opposing it. And then below that, you can see the velocity, the position update form, and the momentum principle. Now conclusions. The model and tracker data show a strong resemblance, as you can see here in the graph. And the model without drag, final position was negative 1.22 meters, and the actual final position was negative 1.135. In conclusion, the drag did not have that much of an effect. The graphs all show a constant, non-constant curved slope, and shows accelerated motion, which is seen by the graph shape. Differences between drag and non-drag models, as you can see, the red and orange lines, they increase the gap as velocity increases. And the model and the actual data differ at the start. Actual data speeds up much quicker than expected, and reasons for this could be human error when I clicked the objects when I was tracking, and possibly incorrect mass of the ball as I did not use a scale. So ways to improve, I can film in a better environment, or I could use a scale to measure the mass of the ball. Each would help the data. So final questions. Which model predicts the terminal velocity? The model with the drag force shows the terminal velocity as you can see here when I graph velocity versus time. The model without drag keeps increasing velocity, but the blue, it hasn't started, it's not that visible yet, but as you can see, there's a big concave up, so it'll keep being concave up until it reaches a minimum value, which makes sense. It will go to that minimum value when force of drag is equal to the weight force. And what happens in terminal velocity if it's thrown downward? So we can look at this mathematically. mg is equal to bv. That's when the forces are equal and it's at terminal velocity. So if we rearrange it, The terminal velocity is mg divided by b. And throwing it downwards would give it initial velocity, and as you can see here, initial velocity does not affect the terminal velocity. So nothing would happen to terminal velocity if we threw it downwards. Thank you very much. My name is Andrew Leonard, and thank you for watching my lab.